Hello, in this presentation, I'll be solving an interesting problem. The problem is that you need to reach for an interview, say at 11 a.m. So, at what time should you be leaving your home and what route should you be taking in order that you are assured, you are certain that you reach your interview place by 11 a.m. Now, more broadly, what the problem is that every city has a limited transportation infrastructure, which is the maximum number of people it can transport from one place to the other. Any more number of people would mean that things would start getting slowly and slowly congestion would happen, or it'll take more time. So what you basically need to do is to distribute traffic at different times of the day, which means some people leave early for something, some people leave a little late. Of course, different people would be having different schedules or different times of appointments, but we need to decide when do you leave so that you can best reach your destination by not having too much of congestion on the road. Now, I'll of course be assuming that there is no kind of communication between the system and the vehicles, so the vehicles do not talk to each other on once on road, as well as people do not enter into the system that I have got an appointment with the doctor at 5 p.m. Some other says that I need to watch a movie at 10 a.m. or you say that I 11 a.m. I'll need to go to a doctor or to the interview. So nobody enters anything into the system and the vehicles do not communicate with each other. Now what's important is that I'm assuming a recurrent traffic, which means the traffic trends, they repeat with time. The trends have got some kind of pattern, and we can learn this pattern from the history in order to assume what we may expect in the future or when we are actually driving on the road. So once I say this, I obviously mean there are two problems. The first problem is the learning of the historical trends or the historical patterns, which will enable me to exploit them, or which will enable me to know what to expect in the future. And once I know that, I'll solve the second problem, which is the start time prediction and route. So if you wanted to go to your destination or interview place at 11, what time, say at 10:15, you need to start, and which route, say this route you need to take starting from your home, in order that you are assured that you can reach by 11 a.m. So this time 10:15 and this route, whatever it is, whichever routes, I'll be calculating in this part of the problem. The interview is one example. In general, what we have, that things like going for a market or a leisure trip, you do not care what time you start, you do not care what time you reach, you're just going to kill time. So it's not at all important when you reach. While if you, for some tasks like catching a flight, if you miss it, the operator will not wait. So you definitely need to reach on time out over here. And middle things are like if you are going to meet a friend, the friend will not kill you if you reach late. He may of course get a little angry if you are too late. Catching a movie, it's okay if you are a minute or too late, but you don't want to be late. You just do not want to miss that starting part of the movie. It's a continuous time scale which denotes the importance of reaching the different place on time, and something like having an interview will of course be, it's more important than catching a movie. You just don't want to be late at all. So it's like somewhere here, it's definitely less important than catching a flight. Now in general, humans solve this problem a lot of time. So let me take in a very particular example, which is of going to your office, which is something that we do every day. Now sometimes humans are better than this system, and hence only the humans should decide when to reach the when to calculate the route and the start time, rather than having this system to do it. Besides these, besides this, it will always be better that the system calculates the time. The system may be much better than the human, or system may be more aware than the human. So let's see what makes the problem of going to the office more capable of being solved by a human than the system. Now, when we go to the office, we basically know what kind of traffic trends do we observe. So, if this is our home and this is our office, this is the route that we have to the office. There might be too many offices out here, and the traffic density in this region may be very high. So, we know that in advance, and hence, when we see a high traffic density here, we are not scared. We already expected that, we already kept a lot of time for that, as well as we should know what are the various possible routes by which we can reach our office. So there might be a route like this, or there might be a route like this, or there might be some other route which diverges from this and it takes this. So we should know what are all these options. It will be really sad that you kept on taking this route your lifetime, which had a high amount of congestion out over here, and it never struck to you that this route might actually be better, that this route might actually not have congestion and might be a little longer, but may make you reach well on time. So you should always know what all different options that you have. Sometimes you may get sick for say a month or two, in which time, let's say this was your selected route, this was your the choice of the route that you had, and in that time, so let's say this was a choice of the route, and then that time there was some construction works going on out over here, and because you were sick for a month, you did not knew that. Now, because there are construction work out over here, the traffic will be very, very slow, and hence the previously whatever time you used to leave will not be true now. So you should know the current trends, or you should know the immediate trends rather than historical trends, or you should be updated with the changing trends. The other thing that we have, that you should have traveled to the office multiple times on this route. Say the first day to your office you used this route, you say good, it takes only 30 minutes to reach my office, fair enough, now every day I'll travel using this route. And while what in general it happened that there was some festival or something, that the other people who go to this office or who go to similar offices, they were not there because of this festival, and you saw a clear route. The next time if you plan only on taking 30 minutes, you will be late because you'll see this excessive traffic. So you should have enough experience, all that. You should have enough experience to know what are the chances of not having excessive traffic, what are the chances of having excessive traffic, what's the probability of there being a congestion, what is the probability of there being no congestion, what's the probability that the road would be moderately occupied, what's the probability that the road would be heavily occupied. So traffic is uncertain thing. You should basically know what's the probability of all these various things happening. And to sum it all up, and that's how we basically go to the office. We every day we try to take in a new route in order to see how good or bad it is. We try to tune in our start time. We try to start at different times. We sometimes we go a little late, a little more late, to see if we are still reaching on time. And sometimes or the other we come into a situation where we say that this is the best time to reach and this is the best route to follow, which ensures that I do not reach very early, as well as ensures that I do actually reach on time. Some other times humans do not follow any kind of system. What they basically do is that, suppose you wanted to go for an interview here, you asked your you asked your Google Maps or your SatNav system, what's the best route? It says this is the best route starting from your home out over here, and you ask how much time it takes. You say it says it takes 30 minutes. So out your interview at 11 a.m. you say that 10:30 I will start. Now what happens at such what happens with such systems is that traffic out this road, say this section of the road again, it might be an office area, it'll change along with time. Morning people will come to office, the traffic might be very slow. Evenings the people will return back, the traffic might again be very slow. Somewhere in the middle, road would be actually vacant, all waiting for yourself as if you own the road. So trends change along with time, and correspondingly your start time should change along with time. So if offices are at 10 a.m., and your interview is also at 10 a.m., you might want to keep an excessive time for this traffic which shows up only at 10 a.m. If your interview is at 12 noon, you might start a little late. So for any system, it's important to capture these trends as the traffic changes along with time, as well as the population is always increasing. More people are using vehicles these days, so the traffic density on road is increasing. So this 30 minutes, maybe after 1 year, maybe 32 minutes, maybe after 5 years, it may become 45 minutes as the traffic changes. The important point here that we would be more associated with, now we say that reaching on reaching an interview at 11 was very important to you, so you should leave home at 10:20. At the same time, if this was your office and reaching at 11 and the office starting time 11 a.m., you could have left at 10:30 from your home. You might get a little late, but it does not matter to you. So the purpose of visit is very important, and what it does is that it plays with the probability of reaching on time. So the probability of reaching before 11 a.m., for this case, you may say that an 80% probability is okay for me. So out there, if 20% of the time I arrive late, my boss does not happens to give a care, he's okay with it. But the probability that I reach before 11 a.m. needs to be very high here. It needs to be of the order of 90 to 95% here, which means that if of the 20% interview you do not reach on time, your chance of getting through are anyways bad. So I need this 90-95% probability. This probability, it depends upon the task, and any system must hence take into account the purpose of visit or the probability of reaching on time in order to give you the best starting time and the best route. Travel, as we know, it's a stochastic process. So if I have a source here and a destination here, I can never say that it takes 30 minutes to go from source to destination. Sometimes it will take 31, sometimes it will take 32, sometimes it will take 28, sometimes it will take 27. So I always have a probability that it takes less than 30 minutes to reach the destination, and that is what we would be working with. So it's a system where the first part of the problem is that I need to learn the historical trends into some kind of data structure like this. And the second part of the problem is I need to use this data structure in order to solve my problem, which is of computing the start time and the route in order to reach the destination on time. So the learning part simply monitors all vehicles. It notices all vehicles running around, and it simply learns the average speed. And because it's a probabilistic model, or because travel is a stochastic model, my average is not enough. I'll basically have to learn the standard deviation or the variation. So for all the vehicles, I'm learning the travel speed and the variation. And this I do it basically for every road. I do it for every day, Monday, Tuesday, Wednesday, Thursday, Friday, and for every time, 10 a.m., 11 a.m., 12 a.m., 10:30 a.m. Once this first part of the problem is solved, I have learned all the information. I would be using a standard graph search in order to calculate the latest start time and the route. Now my objectives are fourfold out for this problem, or for the second part of this problem, which had to do with the query part of it. My first objective is that I need to start as late as possible. So let's say I had my interview at 11 a.m. I do not want to start at 7:30 in the morning, waking up early and going up for the interview. Home is believed to be an easy place, so I need to start as late as possible. So I need to basically calculate this start time, which is as late as possible. 10:40 is better than 10:30, is worse than 10:20. I need to select the fastest route. Roads are always inconvenient where people actually need to drive. So a route which takes 30 minutes is always preferable to the other one which takes 40 minutes. So I'll be calculating the fastest way to reach the goal. In case of an early arrival, so if I had my interview at 11 and I do reach on time, I do not want to wait for 45 minutes, 1 hour, which is a problem many people face who actually start a lot early. A 5-6 minutes waiting time is okay, but I do not really want to wait for very long. And the last factor in my objective function is that I should be assured that I reach by 11 a.m. So my probability that I reach before 11 a.m., it must be as high as possible. It may be 90%, it may be 95%. 95 is of course better than 90. It should be as high as possible or as close as possible to 100%. It's very difficult to get 100% in transportation problem. So if I have my source and I have a destination here, whatever time I decide to start from here, very bad traffic congestion may happen, too many vehicles may be on road, anything might happen. So my probability needs to be as high as possible. It will be very difficult to make it 100%. And that's a graphical representation for the first part of the problem, which had to do with exploiting the recurrent trends or learning the recurrent trends of traffic and storing them into a data structure. So I have got in some interesting agents out here. Each one of these arrows is an intelligent agent operating in a road network graph or transportation infrastructure like this. What this agent does out here is that it observes all these vehicles coming. So these are 1, 2, 3, 4, 5 at this instance of time. There will be more later. It observes all of them coming and it simply learns the average speed and the deviation. So for each of these vehicles, it will learn all these metrics. As vehicles keep pouring in from here to here, this agent will observe when did they leave here. This agent will observe where did they come here. So let's take this very example out here. Suppose at 10 a.m. it left here and 10:05 a.m. it was recorded here. So it will record the average speed and it will also monitor for the standard deviation. The concept that I have floated out over here are of similar days. Now Wednesday and Thursdays, we obviously know that they'll have a similar kind of traffic. Morning people will go to the office, evening they will come back. Some regular percentage of them may go for the for marketing, some may go to the markets, they may go for shopping, some others may go for leisure making, but more or less the traffic would be similar. While Wednesday and Friday will be very different. After work, more people might want to go to restaurants and for shopping and all. So Wednesday and Thursdays have been clubbed together as one day or one similar day. What it basically does is that I had to learn the parameters or the average speeds for all the days and for all the time. So Monday, Tuesday, Wednesday, Thursday, Friday, and 10, 11, 12, 12, 5, 12, 10. I had to learn it for all the days, for all the time. The moment I club 2 days into one, I have lesser parameters to learn, and lesser parameters to learn is always easier. Furthermore, there would be more data. There will be Wednesday's data and there will be Thursday's data. So there will be more data available, and more data is always good thing in learning. And similarly, I say that time will not be time. It will be time in buckets of 10 minutes. So I'm assuming that 10 a.m. to 10:05 a.m. the traffic is very similar, and say 10:06 a.m. to say 10:11 a.m. to 10:21 a.m. again the traffic would be very similar. So in buckets of 10 minutes traffic is assumed to be similar, and again the same thing happens, that if I'm clubbing in traffic in buckets of 10 minutes, I'm reducing the parameters. Reducing parameters means lesser parameters to learn. It means more data available to learn. But I cannot say that I'll club in say traffic from say 10 a.m. to 11 a.m. And why cannot I do that? Suppose 10 a.m. to 10:30 a.m. is when people go to the offices. So normally what I would expect, there'll be a high traffic congestion in roads nearer to the office around 10 to 10:30, and around 10:40 something that would happen is roads would magically become very vacant. Only the regular casual movers or people who are coming very late will come. So traffic is very high here and traffic is very low here. If I use a bucket of 1 hour, this is something which cannot be tapered. So that is how the bucket needs to be decided. It cannot be too large, it cannot be too small. And out there in any system that I have, this is which on observation based systems, which basically record one vehicle coming up from this agent to this agent, which record in one vehicle coming up here and add this vehicle's data into the pool of data to be learned. This is a very standard equation where I add in my new observation into my old average speed, which gives me my new average speed. And obviously there's one factor here, which is learning rate. A very high learning rate, what it means is that if a group of vehicles were there out here who were casual visitors to a place who just wanted to look around and hence they were driving very slowly, this agent will see all these vehicles and it'll learn immediately. And it'll now say that the average speed between these two agents, or the average speed for in this road, is very low, which is false. These people wanted to travel slow. They weren't actually traveling slow because there was high congestion. What this agent with high traffic, with high learning speed would falsely record is a low average travel speed between this. So the learning rate can never be very high and learning rate can never be very small. What happens in small learning rate, suppose there was a little accident that happened out over here, which blocked this route completely. Or I'll take in a better example. Suppose there was some permanent construction going on over here. Now vehicles would take in a lot of slow time in order to reach here. So every vehicle that uses this road will take in a very long because there's some kind of permanent construction going on over here. While what this agent would observe with a low learning rate, it'll simply learn too less. That means it'll take in a lot many days for this agent to know that there's something wrong in this road and the average travel speed is very low. So if you ask this agent, can I use this road, it'll say that yes, very good travel speeds, while the actual travel speeds are not good because of this construction going on. So the learning rate cannot be too high, it cannot be too low. And of course, what I showed in the previous slide, which was the slide here, there was one agent at every intersection, is this kind of system. There's obviously an alternative, and that alternative is that I have got a road network graphs somewhere like this where there are various roads. There's one agent that I place centrally that monitors all vehicles, that learns it or everything, records everything, stores everything, so everything is centrally located. Now these are two very extreme systems, the decentralized system that we are following here and the centralized system. What happens in a centralized system is that the first part of my problem was learning the travel speeds and the second part of my problem was the query. So let's say in the second part of my problem, I need to ask the agent at what time do I start and what route do I take in order to reach my interview at 11 a.m. I will ask this central system out here who knows everything. Basically, he knows everything. This agent will compute and it will return me the answer. So I only need one connection. I only need to connect to the central agent out over here, which is good. Every connection in networking takes some time to be formulated. But the bad thing that happens is that there would be thousands and thousands of people like me who will all query this agent at the same time, and because there are some thousands of people querying this agent at the same time, so there are too many requests that are going in out over here. This agent is performing a graph search, which was to be performed in my second part of the problem or in the query part. It'll take time to cater to one person and there are thousands of them. So you would require very expensive, very high-end computing infrastructure, and the approach is clearly not scalable. If this turns to 10,000s, which happens in a city, kind of in a metropolitan kind of scenario where where there are tens and thousands of vehicles, this infrastructure, it clearly collapses. So what is has been proposed over here is a decentralized system wherein again there is an infrastructure which is like this. Now what I do in my query part, this was presented for the first part of the problem. In my query part, I am here saying that I need to reach my interview at 11 a.m. Now I know that what are the competing routes that make me reach destination. So here, let's say this was my home and this was my interview place. So I say there is this route looks good, this route looks good, and this route looks good. All the other ones are clearly incompetitive. So I'll be making in so many connections, 1, 2, 3, 4, 5. In order to calculate which route is the best, I need to query all these agents multiple times. So there are too many connections to be formulated, which is bad. I mean, each one of these connections will take a long time. And after connections have been made, I can get all the data and I can calculate the best start time and the best route. However, this little infrastructure drawn out here will be a very small part of a very rapid infrastructure out here. So there would be agents out in the other parts of the city like here. Now they are clearly uninfected. I'm not even querying them. I'm not even asking them for anything. And hence, this little agent out here needs to cater to the queries of only few vehicles which are in this area or which need to travel at places in which route it possibly would be coming, or in the competitive routes of which it would possibly coming. So every agent, it caters to the need of very few vehicles, and hence the approach is scalable as compared to the other approaches. So here I have that although multiple connections would be required and time would be very large, but the computation is scalable, it's spread across the agents. And again, in learning one, something that might happen when we practically do such kind of system, many times, say this was the route, I had an intelligent agent placed here, a vehicle here met with an accident. It got met with an accident. There was a temporary accident. As a result, some of the vehicle had to stop to give help. Some men had to be called. The other vehicles also became very cautious. They started driving slowly and slowly. Some seeing what's happening out here. Now, when this agent observes all these vehicles, it does see that there is it observes that the driving speeds have reduced very much. Say the average car used to take in drive at 30 miles per hour. These vehicles are now driving at 10 miles per hour. So there is something wrong. Now if I learn this 10 miles per hour even with a very low learning rate, it's a lot of difference between 30 and 10. So there is definitely something happening. This agent of course is not intelligent enough to see that an accident happened. It only sees that God knows why, but the vehicles earlier used to travel at 30 miles per hour, they now travel at 10 miles per hour. So if I observe such kind of large differences out here, I'll simply pause my learning. My learning rate would say that instantaneously something might have happened, an accident like this, or some other reasons because of which they are non-recurrent immediate trends which will clear in future, and that's what we expect in such kind of scenario where there was an accident. After people moved it up, vehicles again started traveling at 30 miles per hour. So after they started traveling at 30 miles per hour, we resume learning which had been paused out over here. Many times we know that a road will be under construction for some period of time, so we can manually pause learning out here. So we know that from on the 5th of July, this road will be under work, so we say that any data recorded on 5th of July is not important because the entire 5th of July this road is under work, vehicles it's under construction and vehicles will travel very slowly. So 5th of July this agent learns nothing, and from the 6th of July normal proceedings happen. The vehicles can of course be told well in advance that there's construction happening and hence avoid this road. At some other times what might happen, there might be something permanent going on over here. So let's say some big construction which will take in a lot of time, or for some other reason some other road might be completely under repair whose traffic might have migrated to this road, so traffic would have suddenly risen. So again this agent here sees that earlier vehicle used to travel at 30 miles per hour, they are now traveling at 20 miles per hour, so something is wrong. For something needs to be, for this sudden change, it pauses the learning, but later it observes that even after a few days nothing happens, so it sees that it might be a new trend that I need to learn, and hence it continues learning and it learns this new trend that now the average speed will not be 30, it will be 20 miles per hour. So that is how we deal with immediate non-recurrent trends that appear in the traffic. We simply pause learning and later resume it. So that was all for the first part of the problem. The second part of the problem is a standard graph search. So I need not do anything. It's any standard graph algorithm worked over a standard road network graph which is available with the transportation authorities will do the trick. It will do the job. The only problem of course is that I have got 4 objective function while my graph search happens only with one objective function. So I need to fuse the 4 objectives into a single objective which will be the entire agenda of the presentation from now on, and that is what is the cost function that I have decided. It is the latest time in order to reach a node, so that I can be assured that I will reach the goal at the time that I need to reach. So all that I am doing is that I needed to go to an interview at 11 a.m. Let us say this was some kind of road network infrastructure, or these were all the various roads possible like this, and my home is somewhere around here. So that's my home. This was the interview place. So if I need to reach this place at 11 a.m. I should be here by a time which is much before, say by 10:50 I need to be here. This much would take me 10 minutes. I should be here by 10:55. This will take me by 5 minutes. I can be here at any time not exceeding 10:35. It will take me at least 25 minutes to go from here to here. So these are the times which are my cost. And obviously once I calculate something from the source, say 10 a.m., it takes me 1 hour at least to go from my home to the goal. This is what is my least start time. So that's what's the cost function that is to be used. And I know that my graph search, once the cost function is decided, once I have some kind of cost function, my standard graph search with that cost function, it returns me some path, it returns me some route, it returns me some trajectory. So using this cost function, I calculate the earliest start time, and whatever this cost function gives me the route will be my desired route to go to the goal. So let's say this is my actual route that I decide to go to the goal. Now, by its very nature, it must be clear that my graph search is not forward, it's backward. In a general graph search, what we do is that we have some source, we expand from the source, we expand from their children, and we keep expanding until we reach the goal out over here. In this problem, what I will be doing is that I'll be expanding backward from the goal. I will be again expanding backward from their children and from their children, and I'll stop until I reach the source. So in place of going from source to goal, I'll basically be going from goal to source, and the reason from that is very simple. I know that I need my cost for the goal, which is 11. I know this. I need to calculate the cost for all the other nodes. I know that at 11 I need to be at the goal. What I do not know, what time I need to be at these nodes, which I can calculate based on this route. I already know from my learned metrics what's the traffic, based on which I can calculate my cost of these nodes. I'll go all the way from the goal towards the source, which will be my latest start time. So because my cost function is known for the goal and I need to compute it for the source, I'll go backward from the goal to the source. Now again, there were 4 objectives and I decided in one cost function, and I said that that does the trick. I fused the 4 cost function. This slide would be presenting how do I claim that. Now basically, if my interview is here at 11 a.m. and this is the route that I take and this is my home where I need to start, I say that maximize the time wherein I start. So let's say start at 10 a.m. That's the maximum latest time that I have calculated. Automatically, if I reach my interview place early, if I reach my goal early, I'll have to wait for the least amount. So if I make this 10:05, I will arrive more late. If I make this 9:55, I'll have to wait for longer. So because I'm maximizing this, I'm at the same time minimizing my delay in case of an early arrival. And in the same way, I'm minimizing my travel time because it's a standard graph search. Because I'm maximizing this, I'm basically having this time fixed. I'll obviously select for the fastest route in order to reach the goal, because if I select any route which takes in much more time, so let's say this took 1 hour and this took more than 1 hour, so let's say 1 hour 10 minutes, the start time by this new route would be 9:50, and clearly 10 a.m. is better. So if I maximize the start time given my goal time fixed, I'm automatically minimizing my travel time. So the 3 cost function are basically the same, or this cost function, it integrates all these 3. But my problem here is something else. My 4th objective, which was to maximize the probability of reaching the on time, is exactly the opposite. So if I have my home here, I have my interview here. If I leave at 10, I'm likely to arrive at 11 with some probability, say 90% or 95%. But if I leave at 9:50, I'm more likely to arrive on time. So ideally I might arrive at 10:50, but the general thing is that my probability of reaching before 11, it might be 90% at if I reach at 10, but because I have kept in an extra slack time of 10 minutes, it might actually now reach 95%. If I leave at 9:30, it might actually reach 99%. Leaving at 9:30 means that I have got half an hour of slack time. If I leave 9:30 out here, for this 1 hour journey, for a journey which normally takes 1 hour, I've now got 1.5 hours. So even if a lot of congestion happens, I will still reach on time. So the later the start time, these objectives are catered to, and the earlier the start time, this objective is maximized. So I've got 2 contradictory objectives that I need to cater to. Now, how would be doing everything that, how would we say that the system still holds or the system is still good? I'll ask the user what is the probability or what is the risk that you are ready to take. So this thing would be entered by the user. So automatically, if it is an interview, the user will say that I need to be sure by 95% time. If it's just for a movie, the user will say 90% would do. If it's a flight, the user will say that I need to be 100% sure. If it's something else, the user will decide this. Now, once the user decides this time, I'll say that I'll calculate this cost function, which is the latest time that caters to this probability. So if in the previous example, if I was reaching at 10 and my user enter 95%, so this 10 a.m. would be calculated such that the resultant route that I get has a probability of more than 95%, or any other node if it has a cost C, or if the time reported is CAM, leaving this goal at CAM should mean a probability of more than 95%. So how I have fused these two objectives, how I have fused these two contradictory objectives, it's something very clear, that I'm saying this objective is fixed by the user. I'm letting the user optimize, I'm letting the user decide one of the objectives, and I'm maximizing the other three objectives that guarantee me this performance as set by the user. So one of the objectives is user optimized, the other three are optimized by the system. So once I know that for any road network graph, the user has already set in the probability of reaching on time, the simplest thing that I can do is a stochastic graph search. And why do I say stochastic graph search? Because for any road like this, what I have is a stochastic knowledge of how long does it take to go from here to here. I have a stochastic idea of how long does it take from here to here. It may take 5 minutes, it may take 6 minutes, it may take 7 minutes, it may take 5.5 minutes, it may take 5 minutes for 5 seconds, or it may take anything 6.5 minutes. So it's a stochastic time in how long it takes reaches from here to here. I can learn this stochastic model which I did in the previous step, and I can use a stochastic graph search. But of course a road network graph is extremely large, and stochastic graph search, they compute an all combination of probabilities for all combination of roads, which gets very time complex. It gets very time complex if the number of roads are very high, while my deterministic graph search is very fast. So I cannot work with stochasticity, I cannot work with probability distributions, I need to work with deterministic this thing. And hence what I need to do is that I need to convert a stochastic problem into its deterministic equivalent, using the fact that the maximum probability has been fixed by the user, that has been already been decided. So in general what I have is, in order to compute, so say this was my goal where I needed to be there at 11 a.m. I'll need to say at what time should I leave this node out here. I know that this distance is d, so the time it takes me to travel from here to here should be distance upon speed, or the average speed. The problem is that the distance is already deterministic, of course. No matter how many times you measure it, it will be the same. The problem is that the speed is stochastic in nature. It may be 30 miles per hour, it may be 35 miles per hour. I need to make this deterministic. That assures me that the user specified probability is catered to. So what I have got, at one end I have got a probability distribution, which is a distribution over the various speeds that I have learnt, that I have from my historic information. At the other end I have got a probability which my user has fixed, say 95%. Based on that I need to decide what will be my speed that I take or that I choose. And once I have got this speed, I will simply say my travel time is distance upon this speed. So the question is only about how to decide this travel speed. And here is something that I have plotted. my learning system was doing, or what my system was doing that I presented earlier, it noted the speed of all these vehicles. It was noting down the speed of all these vehicles. This agent was noting all these travel speeds. And what I do is that I plot a probability distribution over the observed speed. So let's say this vehicle had this speed, this vehicle has this speed, and so on. I add up all the vehicles that show the speed, and let's say it happens to be this. I add up all the vehicles, let's say it happens to be this. I add up speeds of all these vehicles, let's say it happens to be this. And I plot this nice distribution over the time. So at any general point here, I know how many vehicles are showing that travel speed. And of course, people would understand that I obviously did not observe all in vehicles and noted down each one of their data in order to calculate this. I've used a standard trick, which is fixing a Gaussian, or fixing a normal distribution, where the average speed that I was noting down is this, and the variation that I was noting down, which is standard deviation, it is this. So I've basically plotted a Gaussian over the historical data. Now I remember what my problem is. My problem here is to find the speed, that is to fix this speed. Or my problem is that given such a stochastic distribution of speeds, where different vehicles show different speeds, I need to fix one speed. So should I pick this speed, this speed, this speed, or this speed? Now there are various things that you can do. Is that I again had a scenario like this, where the agent here observed different vehicles coming up with different speeds. One thing that I can say is that whatever is the highest speed that I observe, I say that let me say that I choose that as the chosen speed. Or let me say that in calculating my time to go for the interview, which was 10 a.m. here, I'm assuming that my vehicle would be traveling at the highest speed which is possible as per this route. So let's say the speed limit, the national speed limit was 40 miles per hour. I say that I'll always be traveling at 40 miles per hour, and this is clearly too optimistic in nature. Speed limit of 40 miles per hour never means that you can drive at 40 miles per hour. And this should obviously be avoided. The other thing that is possible is that I say that this agent once saw a vehicle that was moving at 10 miles per hour, and therefore I say that in my entire calculation for this route would be based on a speed of 10 miles per hour. Some vehicle in history was following that. For my interview, I don't want to be late. I want to be very, very, very safe. And hence, because in history no vehicle has traveled this road at less than 10 miles per hour, 10 miles per hour means very good. And practically, obviously, what it means is that I'll reach in too early. So if my route by 10 miles per hour was 7 in the morning, I'll reach at 8 in the morning over here. And for 3 hours, I'll be doing nothing, I'll be waiting. And what was the problem? That I assumed that I'll be traveling at 10 miles per hour, while my average speed may be well over 30 miles per hour. So this is too pessimistic. And we've got intermediate. Now the average is of course what we generally consider. We generally say that I travel this route many times. On an average it takes 30 minutes, and that's what I'll keep. So for an interview at 11, I'll travel at 10:30. That is what it keeps. I've traveled that road many times. It's always taken me on an average 30 minutes, sometimes more 35, sometimes less 25, on an average 35. But then we'll of course say, or your neighbors would say, or people around would say that interview is something very important to you. You do not want to be less. You do not want to be late. So although at an average it takes 30 minutes, you keep 5 minutes extra. That anything bad might happen, so you keep 5 minutes extra, and hence you say that let me take 35 minutes. So what we are doing here is that normally we would have taken an average, but because we are going in for normally we would have assumed the average speed, But because we are going for an interview, we'll be a little pessimistic. We'll assume that bad things might happen, which generally do not happen, and we'll take a speed which is just lower than 30, which is just lower than the average speed. So that is what I have shown out over here. That normally we would have considered the average speed out here, but this is the speed that we would be choosing, and this is of course the risk region. This is the slack time, or this is the extra 5 minutes, or this is the extra time that I have kept because it is for a particular road. So I'll change the terminology. I'll say it because this is the extra speed that I have kept, or this is the risk that this is the speed dependent on the risk that I have kept. So this is what is the risk region. In any Gaussian, this is called as a deviation. That's what's the standard terminology. So I have kept my risk region as multiplication of two factor, which is alpha, which is a user set parameter, and my deviation here. So in general, what would happen is that I have kept it as multiplication of two terms. And why have I done that is something very obvious. If my alpha is large, then what happens is that I'm going in for something like an interview or something like flight, where I need to keep more resistance to more risk. I need to keep more slack time. I need to keep more extra time. I am very conscious of reaching early. I need to be assured that I reach early. I do not want to be at any time be late. So that's what my high alpha means, that my risk region would be large, which means my chosen speed would be low, which means ultimately I'll have more time. And if my deviation is large, which was learned from the probability in my learning stage, so this is the distribution with low deviation, and of course this is the distribution with large deviation, where this is the mean and this is the deviation. So if my deviation is large, it means vehicle in that road vary a lot in their speeds. Some travel at 15 miles per hour, some travel at 20 miles per hour, some travel at 25 miles per hour. There's a lot of ambiguity in the vehicle speed at that region. And what that means is that that road is very uncertain. Maybe some tourists are going who travel very slowly on that region. There might be a nice scenic beauty, or maybe that road has some natural uncertainties where some drivers become very cautious and they slow down a lot. So there is something about that road where vehicles have a very high amount of differences in their natural driving speed. That means that road is very uncertain. And because that road is uncertain, we do not want to use it for a thing like an interview, where we want to go in roads where we know what would happen, where we know what would be the travel time, where we know what would be the travel speed. So again, high deviation means that those roads should be avoided, or a larger risk time should be taken, and that's what will happen. A high deviation, a high risk region, and a low chosen speed, and a high risk time being already accounted for. And once I do this, there is again a problem that sometimes outside your house, or sometimes far away from your house, there might be a road which is rarely used. This road is rarely used. Nobody likes to go for some reason by this road. If nobody likes to go on these roads, unlike these roads which are heavily packed, which are highly congested, my data will be too less. My data for learning will be too less. And whenever my data for learning is too less, neither mean can be relied upon nor deviation can be relied upon. Now, if the deviation is large, that is something desirable for me, because high deviation already means that the road is very risky. Either take a lot of risk time, either account for that already, or do not consider that road at all. But the problem is that if only two vehicles travel that road, and only those two vehicles were used for my learning, and they both traveled at approximately 25 miles per hour, So my mean would be 25 miles per hour and my deviation would be close to 0. If there is only one vehicle, it will actually be 0. Now that does not mean if I travel by this route, I should expect 25 miles per hour, which is what my mean and deviation tell me. I should expect something more. And hence my system fails, and the fix to the system is of course that I keep the minimum deviation fix. So in such kind where the average speed was 25 and the deviation was close to 0, I say that I'll not use deviation 0, I'll use some fixed deviation of sigma min and I'll use it for my calculations. So basically using these two slides and by that very magical formula of the chosen speed, my entire problem was only about choosing speed. Rest it's a standard graph search function with the known calculations. By only by fixing in alpha in that formula, in that magical formula of speed equals to average speed or average learn speed minus alpha times deviation, what I have done is that the user fixes in alpha, he uses our systems, and then my system gives him the start time and the route to be used. If the user is very conscious, he'll fix in more alpha and so on. The problem is that I wanted my user to give in as an input a probability instead of alpha, and then the system works. So I need as an input probability, which then converts into alpha, and the way of doing that is very simple. I draw a graph between alpha and probability for any particular region. I simulate a large number of regions. I say what alpha give me what probability. It will come up of a graph like this, and I can simply convert graph into probability. In fact, it will come up, a high alpha would ultimately mean more risk, so it would ultimately mean probability of reaching on time. So if I'm considering the word probability here, the graph would be actually like this, and these are the results that I have. Now what each one of these it denotes is that I'm basically simulating vehicles for a particular alpha, and I see how much after the ideal reaching time or how much before the ideal reaching time do they come. So some vehicles would come a lot earlier than the reaching time, some vehicles would come a lot later than the reaching time, some vehicles would come around this time, which is just comfortable. It's there's some waiting time, some would come exactly at the waiting time. I add up all these vehicles, I take the percentages, and I get this distribution between the percentage of vehicles and the deviation from the ideal reaching time. So a vehicle reaching here means that it had to come at 11, but it came at 11:05, or it came at 11:15, or it came at 10:55, which means 5 minutes late. That's before this black line over here. So all these vehicles are late. All these vehicles are late, which is a bad thing. They never had to be late. That was my control objective. These vehicles are bad because they've reached too early and they have to wait for all this time. They have to wait for this large amount of time over here, and this is a comfortable region where I want my vehicles to be. In fact, if they reach here, these are the best vehicles. They came bang on time. So as would be observed, as I increase alpha, less vehicles get late. So when alpha was 0, so many vehicles were getting late. When alpha was 0.25, some vehicles got late. When alpha is 0.5 out here, very few, practically no vehicle is getting late. And so on. As I increase alpha, less and less vehicles getting late, which is natural. By increasing alpha meant taking more lag time, taking more risk time, assuming lower speeds, and hence the probability of getting late is low. But as the probability of getting late gets low, I obviously mean one thing happens, that I start getting vehicles start reaching too early, and if the vehicles start reaching too early, then they have to wait for a long time. And again, it's a stochastic system, it's not a determinate system, so I'll have a probability distribution like this rather than for every alpha having a particular point out here. and these are for the other intermediate values of alpha. This was at some intervals here, and all the intermediary values have been plotted and out over here. So it's the same graph basically and shows the same trends. And I in the previous I said that I'll be plotting a graph between the probability of reaching on time and between alpha. What I have basically done is that I've calculated between 1 minus probability, which is the percentage of vehicles getting late, and alpha. So it's a converse graph, and that naturally shows trend like this. If I increase alpha, more and more vehicles, lesser and lesser percentage of vehicles to start getting late. That means they are taking more slack time. And if only for the vehicles getting late, if I add up how much time did they get late, or if I add up the lateness time, so let's say 5 vehicles arrived late, the destination had to be reached at 11 a.m. for all these vehicles. One reached at 11:01, the other reached at 11:03, the other reached at 11:10, the other one reached at 11:05. So I add up all the lateness, 1 minute here, 3 minutes here, 10 minutes here, 5 minutes here, and I plot it out over here. So I see that not only is the percentage of vehicles getting late getting reduced, the vehicles which are actually getting late by lesser and lesser time out here. Now an interesting observation of all this is that suppose I take in 3 examples. Catching a flight where you need 100% assurance of reaching on time. If you an interview where you are good with 95%, and catching a movie where say 80% is fine enough. 20% movie, if you are a little bit late, it does not really matter. Now a practical observation is that with flights we go in very early and we wait maybe for even half an hour. We take that extra half an hour. For an interview we go early and we normally wait for 10-15 minutes, and we take in those 10-15 minutes. And for a movie we basically go bang on time. If we are preparing with early, maybe 5 minutes early, but we try to go bang on time. We do not really take in a slag time. So a 5 minutes here rises up by for only some 15% increase in probability. For only that small percentage in increase in probability, it reaches to 15 minutes here, and it gets atrocious out here where it doubles for only a 5% increase in probability. That's a very practical observation, and that is what was basically shown out over here, that for increasing the percentage by a little amount, there's actually no consolidated graph that plots in percentage at one end and my early arrival at the other end. So there's no consolidated graph between percentage and the early arrival. But if we add up if we study closely these two graphs, we would come to know that the same thing happens out there in the system. For a little increase in percentage, I need to wait for a lot longer. And that would be clear out over here that for this graph and this graph, they vary a very little in the percentage of early late arrival, but look at it how much the time to wait has changed. And this has of course the best, and look at it how the time of early arrival has increased. So I'll have to wait for terribly long for that little increase in percentage of early arrival. And that would be all for the presentation. Thank you.